I'm going to write the title down, but I'm not how to pronounce it. We're going to have a little discussion about that in a minute. Something sums in the trapezoidal rule. I'm about to tell you. Okay. I'm going to take a little detour, and I don't want you to write this down, so I'm putting this on a separate sheet of paper. Okay. Yes, the camera's on. How do you say that? Huebner. Why don't you say Huebner? Doesn't it look like, isn't that the word Hugh? Why don't you say Huebner?
Because it's like just what we've learned.
Just what you've learned. I actually taught with a lady who had this for her last name, and she pronounced it Huebner. So when I moved down here, I thought everybody said Huebner, and they're all saying Huebner, and I'm like, Huebner? That's kind of weird. Okay, what about this right here? We all know it's Bernie. You go up to Dallas, they'd look at that and they'd say Bourne. Like the Bourne Identity or something like that. But we know it's Bernie just because we live here. Okay? Does anybody know why we say it that way? Okay. I'm about to teach you a little lesson. It's German. Okay? In German, whenever you have a double consonant, you say the second one, not the first one. Okay? They just said a young man's last name on the announcements. I had his older brother. I never had him. You would think that would be spies because you've seen that word in books, but it's not. In German, it's spies. Because they said spies. They said spies instead of spies. Okay? I had these two young men. They're twin brothers. You would think that's Brumer. No, it's Bremer. The U is silent. Okay? This guy's name is German too. Riemann. It's pronounced Riemann. Riemann. The E says E. Riemann Sums. Okay? So now you know. Riemann. Just like Huebner. Riemann. Okay, and here's the other thing I want to talk about. How many of you remember this symbol from last year? You remember this?
Sigma.
It's called a sigma. Exactly. It's a Greek letter. It is the capital Greek letter E. And it always had something like, looks something like that. What do you do with that? Do you remember?
Take the sum of the whole thing. You plug in like the I equals 1.
Right.
And then the top is like the sequence.
You go up to 5.
You go up to 5, exactly. So this would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Do you remember that? Okay. So if I had I equals 2 to you, say, 4 of the square root of I, what would you write? Square root of 2 plus the square root of 3 plus square root of 4, and then you add them all up, right? Okay, you're going to see this again today in the notes. So I wanted to make sure that you remembered how it works and what it meant. Okay? So now, let's have a talk about Riemann sums. We're going to be changing gears a little bit because trapezoid, is trapezoid an algebra word?
Geometry.
It's a geometry word, isn't it? You remember what a trapezoid looks like? You're going to see them again today. So we're going to be talking a little bit less about algebra today and a little bit more about geometry today. And we are going to be talking about geometry for the next couple of weeks. Not hard geometry, easy geometry. Okay? No. I know y'all remember Agile Mind, yes. Okay? Now, Riemann sums and the trapezoidal rule are used to find the area under a curve. All right. First semester, when we learned about the derivative, we were able to go from going and finding only the slopes of lines. Now we can find the slopes of curves. So we've expanded what we've been able to do in the past. In the past, the only thing you could find the slope of was a line, but now with calculus, you can find the slope of a curve. Second semester, we're going a geometry route. Instead of finding the area of shapes that we know, what are some of the shapes you can find the area of? Squares, circles, rectangles, triangles. That's volume. Parallelograms, right? Trapezoids, things like that. With calculus, you can find the area of anything, any shape whatsoever. A blob, you can find the area of a blob exactly using calculus, okay? And we're going to learn how to do that. You can also find the volume of anything, by the way, even if it's oddly shaped, okay? So, the first thing that they figured out was there's ways to estimate it, okay? So here's what I need you to do. We're going to have 4 examples here, and they need to be drawn rather accurately. So we're going to put 1 and 2 here. I want you to draw a first quadrant, pretty decent size. And then come down and do a 3 and a 4. Same thing. This is going to be like the derivative of e to the x, copy paste. I want the same thing 4 times.
Is this just plugging into formula?
Pardon me?
Is this just like plugging into formula?
It is for today. Yes, it is. Okay? So 4 first quadrants. Now what I need you to draw is the exact same curve in 4 quadrants, and they have to be the same as mine. You're going to draw a piece of graph that is increasing and concave up. What's that going to look like? Increasing and concave up. Kind of half of a parabola, all right? So go ahead and put a dot. I'm going to do it 1 line up, and then draw increasing, concave up, something like that. And make them exactly, try to make them exactly the same for all 4 of them. As much as you can. After you finish that, I want you to go to the end point of each one and drop a perpendicular down to the x-axis. Today we are going to talk about the 4 different ways to estimate the area of this shape right here. Now, does that look like any shape you've ever found the area of before? Probably not. What makes it hard is the fact that one of the sides is curved. Okay? Everything that we've done, the only thing that we've been able to find the area of that was curved in the past is what? A circle. Everything else has been a straight line figure. Okay? Say, yeah, you do like the area of the square. Kind of looks like it could be done with a triangle. We're going to talk about the different ways to do it. Okay, we are going to divide each one of these into what is called 4 sub-intervals. Okay, so I want you to go to the x-axis. I want you to divide this width into fourths. So basically, estimate where the halfway point is and draw a mark, and then do half of each of the 2 pieces. So right there and right there. And do that for all 4 of them. Okay. I'm going to do on this first one a little bit more math to it. From each of the marks, I want you to go up to the curve and put a dot. Actually, you're going to have to do this on all of them. So let's go ahead and do that on all of them. Right there, and right there. Now, we're not going to label it on all of them, but we're going to draw them on all of them. All right. This first dot that's on the y-axis is going to be called y sub 0 because it is the initial y value. The next one over is y sub 1, then y sub 2, y sub 3, y sub 4. We're only going to do that on the first one. Okay? Are each of these equal width? Are each of these equal width down here? We're going to call the width of each of these B. Just put a B under the first, right between the first 2. Okay. Now, I should have said this earlier. You may want to get another color out. I'll wait just a second while you do that. It's up to you. Should have said this before I started notes, but I forgot. Okay. What we're going to do for this first one is we are going to estimate the area under here using a shape we can take the area of. And we're going to use rectangles. So the first method is called right rectangles. Right rectangles. Okay. Now these rectangles are going to be sitting up on end. Okay. So go ahead and draw with your other color lines going straight down like so. Now, the top of this right now is not straight. It needs to be. Okay. So when I use the word right rectangle, of the two sides of the rectangle, I use the y value that is on the right to determine the height of the rectangle. Which one of these two y values is on the right? Y0 or Y1? Y1 is. So Y1 is going to determine the height of my rectangle. So I'm going to draw a line straight across to the y-axis from Y1 and shade that in, like so. That's my first rectangle. Okay, in the next region, which one of these two y values is the right one? Y2. So Y2 is going to be the height of my second rectangle. Do you see what I just did? Draw straight across from Y2 until I hit Y1 and then come straight down. Shade that in. Between Y2 and Y3, the right one is Y3. So I go straight over from Y3 till I get to Y2, drop it down, shade that in. And then between Y3 and Y4, the right one is Y4. So I go out from Y4, drop it down, shade that in. Now, if I add up those rectangles, that would give me an estimate of the area under that curve. Would it be an overestimate or an underestimate in this case? Overestimate. Okay? So what I want to do now is come down to the bottom of the page, and I want to write right rectangles, and I want to write the exact formula of what this would be. Move it up just a little bit. So the area would be of this first rectangle. What's the formula for the area of a rectangle? Length times width, or we're going to call it base times height this time. What is the base's length? What did I label it in my picture? B. Times, which one of the two y's determined the height? Y1. Y1 did. So B times Y1 plus, what's the width of the second? B again, times Y2, you all see that? Plus B times Y3 plus B times Y4. Now I need you to do just the four of those, okay? So, do all of them have something in common I can factor out? A B. So B parentheses, Y1 plus Y2 plus Y3 plus Y4, which is the same thing as B times the summation I equals 1 to 4 of Y sub I. Now, after you write that down, think about it. Does that mean the same thing as what I wrote above it? Yes, it does. Because you plug in the 1, then the 2, then the 3, and then the 4. And there it is. Yeah, that's a lot shorter. Because what if I had 10 rectangles? Would I want to write out Y1 plus Y2 plus Y3 plus Y4? No. That's a lot quicker. The only thing that would change for that was the 4 would be a 10. Right? Okay. Well, I went a little farther than I wanted to. So I'm going to draw a line because I've got to put something over there. All right. Any questions on the right rectangles? Okay. Let's move to number 2. Number 2 is left rectangles.
So, Ms. Bell, how do you account for the overestimate for the left rectangle?
Okay. Every time you do a right rectangle, you know it's going to be an overestimate. But let me ask you this. What could I do to the rectangles to make the overestimate smaller?
Make them square. No,
Decrease the base. If I made them skinnier, it would be less of it sticking out. because there would be less of a gap between the points. Does that make sense? Yes. More rectangles means better estimate. Well, we're just doing 4 now to make the formulas a little bit easier. Okay? So, for left rectangles, we do the same thing, except we use the left of the 2 points to draw the rectangle. So how is this one going to look different? It's going to be under. So these 2 dots, I'm going to use the left one, which is that one. So this one's going to be right there. Of the next 2 dots, I use the left one. So you go straight across. And of the next 2, I use the left one. So I'm just doing that right there. And of these 2, I'm using the left one. So I'm doing that right there. So this one is in this case, it's an underestimate. It's not always going to be an underestimate with lefts. It depends on the way the curve goes. Now, those of you who are really good at visualizing things, how would the curve have to change for the left rectangles to be overestimates? Say it again?
It'd have to be like a decrease.
It'd be a decreasing graph. If it was decreasing, the left rectangles would be underestimates. Overestimates, excuse me. I said it wrong. Okay, so let's go to the bottom and let's write the formula and see how it's going to change. So for left rectangles, I'm going to have to cram this in here because I went a little too far over the page. Is the base still B? Yes. Yeah, I divided in the same number of units. But what is my first height? Y0, Y sub 0, plus B times Y1, plus B times Y2, plus B times Y3, which would be, oh wait just a second. Hang on just a minute. I'm getting there. Plus Y2 plus Y3. B times the sigma. What were you going to say, Aaron?
The I equals 0 and then 3 goes on top and y sub I.
Y sub I. Very good. Okay. So, do you see that these 2 sigmas are very similar? Okay. So, the general form for the sigma, we're going to change the way it looks, but we're going to change the B to a delta X. Bless you, what does delta mean in change in X? Well, think about it. Isn't our B value just a change in X, and depending on how many rectangles we cram in there, it's going to be a different change? Okay. So the area will be the sum I equals 1 to n, however many rectangles we have, of y sub I, but instead of the b in the front, we're going to put it on the end times delta x, and you'll see later why it does that. This right here is the Riemann sum. That is a Riemann sum right there. That's what Riemann came up with it. Yeah.
Why is it I equals 1, the rectangles equals 0?
Because in this case, the number, okay, if this is 1, this was 4 rectangles, right? And the top number was a 4. So if this first one is a 1, this n always represents the last rectangle.
Yeah.
In the left rectangle, for example, that would actually be I minus 1 down here.
Okay.
Does that make sense? Yeah. That may change a little bit. It may be I or I minus 1, depending on how you set it up. Okay.
So,
Yes?
the I just means what you start with, right?
Right.
Okay.
It could actually, I thought about writing it as I equals I, but that would be a little confusing because n is always the last one that you're, however many subintervals you're going to have. Okay? So this could be y sub I or it could be I minus 1, depending on if you're doing left or right.
Okay.
Okay? So, we're actually not going to be using this much. I'm just kind of introducing you to it. It's kind of like say, hi, glad to meet you. Might see you again someday. But we're going to do it a different way. We're going to be dealing with data, and it makes it a lot easier to do. Okay? Is everybody done writing this down so I can go on to the next page? Oh, wait, actually, no, I'm not going to the next page. I need to go back up here and do number 3. Number 3, we're not going to be writing any formulas for these. We're just going to draw them. The third one is called midpoint rectangles. And I'm just showing you what they look like, because we're going to come back to midpoint rectangles later. Okay? Has anybody got a guess as to what I'm going to do with a midpoint rectangle? Right. So, but instead of using y0 or y1, I'm going to use the middle of those two. So find the middle, go up to the curve. That's the height of the rectangle, the midpoint between the two. So in this case, because they're almost the same height, it's pretty much the same thing right there. But as you move up, it's going to be very obvious. Find the middle between the two on the x-axis, go up to the curve, and then draw your rectangle with that for a height. Find the middle, go up to the curve, like so. Now this one has the best estimate of the area under the curve so far. Do you agree with me?
Yes.
Why is it better? It's all just a little bit over and a little bit under, and they almost cancel each other out, don't they? In this case. Okay, so far that's the best. Any questions on the midpoint? Just kind of what it looks like. I'm trying to give you a mental picture so when you do the problems, you kind of see what's going on in your brain. Okay, here's the last one. Last one's the trapezoid. So everything we've done up to so far has been rectangles, trapezoids. Okay, those of you who are real big geometry, like geometry as opposed to algebra, does anybody remember what the definition of a trapezoid is?
It's got two parallel lines and then two, if they're not congruent, equivalent length.
Okay. They could be equivalent length. They're not parallel. That's the whole point. A trapezoid only has two sides that are parallel. The other two are not. So, like, you're used to seeing them where these two are parallel and these two are not.
But the outside two have to be congruent, right?
No, they do not. They do not have to be
But if one was
congruent.
bigger, wouldn't it be a slanted line then? It wouldn't be parallel.
Okay. Let me show you. Okay.
Because it can be like a straight line.
That's a trapezoid right there. Yes. Okay. We're used to seeing trapezoids like this. That's a right trapezoid, actually. When these two sides are congruent and these two sides are parallel, that's a right trapezoid. That's just a standard trapezoid. Okay? Now, you're used to seeing it where the two parallel sides are horizontal. But here, our trapezoid is going to look like this. It's going to look like this, where the parallel sides are vertical. We're going to stand it up on end. Okay? So, drop your lines down from each of your interval markings. And so this slanted line will be created by connecting the two y values on the end of each one. So this one's almost straight across. So there's that one. Then you connect these two. There's that trapezoid. Then you connect these two. There's that trapezoid. And then you connect those two. And there's that trapezoid. And that actually is the best estimate of the area under the curve. We're going to talk about its formula after we've done a couple of left and rights, because it's a very different formula than this one right there.
Why would you always use a trapezoid?
Depending on what, yeah, it's more work. It's more work. It is the most accurate, but it is more work. And actually, when we get to the calculus end of it, the calculus is 100% accurate. That's about 95% accurate, depending on the shape of the curve. Okay? But you need to know how to do all of them. Okay? Any questions on this page before I move on? Okay. moving on. Changing my notes. Okay. I'm going to introduce you to a new term that we're going to go into more detail on in a few days. And this is called a definite integral. We did indefinite integrals last Thursday. Now it's time to say hello to the definite integral. Hello, definite integral. How are you? Okay. The reason I'm introducing it now is because the worksheet uses this notation. We're actually going to learn how to mathematically do it later, but you need to see it. It is an integral symbol like before, an f of x and a dx like before. The one difference that makes it definite is that you have a number or a value at the bottom of the integral symbol, which is a, and one at the top, which we call b. This is read the integral from a to b of f of x dx. That's how you say it. The integral from a to b, you always say from bottom to top. And what it means is the area under f of x from x equals a to x equals b. That's what it calculates. The way you say it is the integral from a to b, but what it's calculating is the area from a to b. Do you do these in physics, C?
Yeah.
You do? Okay. Now, the a and the b are called limits of integration. The a and the b are both limits of integration. So I'm going to draw a big arrow going around like that, because I don't have another line to write it on. I'm not going to be able to fit the rest of my notes on this page. Okay. Let me show you what the worksheet is going to look like. I need you to draw me a table of data. You're going to put 6 values on here. So 1, 2, 3, 4, 5, 6. So you need 12 boxes. First box is going to be x and f of x. 0, 2, 6, 11, and 18. 6, 13, 15, 22, and 30. Okay. Are we ready to move on?
Yes.
Okay. Everybody else ready to move on? So I'm still drawing. Okay. The question says, estimate the integral from 0 to 18 of f of x dx using a right Riemann sum. I don't know why I capitalized right, but I did. With 4 subintervals. I'll stop and let you catch up with me. Estimate the integral from 0 to 18 of f of x dx using a right Riemann sum with 4 subintervals.
When you say right Riemann sums, does that mean right rectangle?
Yes, right rectangles.
I mean, overestimate.
Are those increasing values? Yes, then it would be an overestimate. You are correct. Okay. Now, this is not hard if you know what to do. Okay?
Be changing those?
Now what?
The distance between the points isn't a constant distance.
It is not a constant distance. Okay. Barrett noticed here that the distance between these points, unlike the one we did over here, is different. Okay? I can't show you both on the same screen. Yes, I can. The distance, the b value here, was the same all the way across. These are different. Do you see that they're different?
Do you just see the overall change?
You have to do each, when this is different, you have to do each rectangle individually. You can't do a shortcut like we did the formula at the bottom, okay? So in this case, because there's only 4, you can go ahead and do it by hand. So, 4 subintervals. If this is 4, 3, 2, 1, and 0 for the y values, it works. So basically, a subinterval means pairs of y values. So can we make 4 pairs here? 1, 2, 3, 4. Yes, we can. That's 4 subintervals. And then for the x's, we pair them up the same way.
You can use the first one.
Right is the second. All right. So, as you do this, especially when they're not equally spaced, you look at the first pair of values like so. What is b?
2.
It's 2. Does everybody see where we're getting 2 from? It's a distance along the x-axis. The difference between the two is 2. So 2 times, which one is the right y value? 13. So 2 times 13 plus, there's the first rectangle. Then look at the second pair of data. What's b? 4 this time, the difference between 6 and 2. So 4 times 15 plus, go to the third pair. It's 5. Do you see the 5? Times 22 plus, no, 7 times 30. You all see what I did? Now get your calculator and add them up. Oh, we're good today. I might finish. Hope you do. What are y'all getting?
406.
406 units squared. Nope. Not yet. No, with data, you have to do it. You don't have a choice.
But there is a way, right? Because I remember doing
There is a way with a function. With if you have an equation, there's a faster way. But if you don't have an equation, this is the only way. Okay. Any questions on how we got that? All right. Number 2. Estimate the integral 0 to 18 f of x dx using a left Riemann sum with 4 subintervals. Period. Estimate the integral from 0 to 18 of f of x dx using a left Riemann sum with 4 subintervals. Okay, I want you to do this one with your table. Left Riemann sum.
All right, Jason. Wait. Are we? Oh, it's
Same data, just a left sum. Right? You've got to write out this step right here. You've got to write that step out. Now think about what's going to change and what's going to stay the same. Have that conversation at your table if you're not sure. What changes, what stays the same? If you think you got it, I want to see it.
I got 293.
Yep. Yes. Yep. Nice. do it. You can do it all as one line. You don't have to type, push enter between them. You can just type it all in one line.
Well, we should be done with them.
And I'm not done yet.
We're going to do 2 more sets. 2 more.
I'm going to go as far as I can because of tomorrow with that assembly. Okay. Did we all get 293? Okay. Are we good? All right, let's move on. Okay, we've talked about left and right. We're going to do trapezoid and then we're going to do midpoint. So let's talk about the trapezoidal rule. Dot, dot. Okay, I'm going to redraw the picture from the front.
We're showing please question when we drew.
Yeah, basically redrawing it because we're going to come up with an equation for it. But I'm not going to shade it. I want to number the trapezoids instead. Let me move this up. I didn't realize I was drawing in the basement here. Okay, for this one, it's important that I've got the Y0, Y1, Y2, Y3, and Y4 right there. Okay, there are many different ways to write the equation of a trapezoid. The one that I learned when I was in school was 1/2 the height times the sum of the bases. Some of them do base plus base divided by, no, times height divided by 2. But the way we're going to do it is because this thing is turned on end, the base, it's really 1/2 the base times the sum of the heights. So that's how we're going to write it. 1/2 B times H1 plus H2. 1/2 the base times the sum of the heights. Okay? So, for the first trapezoid, define the area of the first trapezoid. It would be 1/2 B, because it's still B. And then what would I put in the parentheses?
Y0 plus Y1.
Y sub 0 plus Y sub 1. Does everybody see how I got that? Okay. For the second trapezoid, is it 1/2 B again? Is the B the same? In this case, yes. 1/2 B, and then what?
Y sub 1 plus Y sub 2.
Y sub 1 plus Y sub 2. And then for the third one, 1/2 B, and it's Y2 plus Y3. And the last one is 1/2 B, Y3 plus Y4. Are y'all with me? This is not too hard.
Yes.
Okay? Now, the area under here would be adding all that up, right? But I'm going to write it in as small of a way as I can, and I'm going to call it T equals for trapezoid. That's just the way I was taught, so I'm going to do it with you too. T for trapezoidal rule. What do all 4 trapezoids have in common? 1/2 B. Let's factor that baby out. How many times do I use the Y sub 0? I have some repeaters in here. I only use Y sub 0 one time. But how many times do I use Y sub 1? Twice. One for the right side of the first rectangle and one for the left side of the second rectangle. So I'm going to put 2 Y1s. What about Y2? Twice again. Do I use all the rest of them twice?
Only 3.
Only 3. And then Y4. Okay. So what if I had 10 rectangles? Which ones would I use twice?
1 through 9.
One through, no, yeah, 1 through 9, and then 0 and 10 I would only use once, right? So basically the rule is the outside ones only get once, and everything in the middle gets twice, okay? So the formula, the trapezoidal rule, no matter how many you have, you always start with y sub 0, always. So it's 1/2 b y0 plus 2y1 plus ... however many you want. Now, and it's plus 2yn minus 1 plus y sub n. Go ahead and write that down, and I'm going to talk about the n's. Okay. How many trapezoids did this picture have? 4. What is my last subscript? A 4. So the last subscript always tells you how many trapezoids you have. So this one's saying if I have n trapezoids, the last number is only used once. The one right before that is used twice, and so is everything in the middle. Does that make sense?